How scientists are turning plastic bottles into hydrogen fuel. Most plastic bottles never get recycled. Of the roughly 70 million tons of PET plastic produced every year, that's the clear plastic in water bottles, food packaging, and polyester clothing. Less than 20% is actually processed after use. The rest ends up in landfills, incinerators, or the environment. Researchers in China think they've found a better use for it: fuel. A team at Inner Mongolia Normal University has demonstrated a process that takes shredded PET plastic, dissolves it in a chemical bath, and runs an electrical current through it. What comes out the other side is hydrogen gas, a clean fuel, and a chemical called formate, which is used in animal feed and food preservation. Both have commercial value. Neither requires new raw materials beyond the waste plastic itself. The plastic isn't just being disposed of. It's being converted into something worth selling. What actually happens inside the device? Here's the plain English version of the process. PET plastic is first dissolved in a heated alkaline solution, essentially a strong base, similar in concept to drain cleaner, though far more controlled. This breaks the plastic into two chemical building blocks: ethylene glycol, the same compound used in antifreeze, and terephthalic acid. Those two ingredients are then fed into an electrochemical cell. Think of it like a battery running in reverse. Instead of storing electricity, it uses electricity to drive chemical reactions. On one side of the cell, hydrogen gas bubbles off. On the other side, the ethylene glycol is converted into formate. The device that makes this work is a specially engineered electrode coated with a material called a metal organic framework, a class of porous crystalline structure that creates an enormous number of tiny reactive surfaces in a very small space. The researchers doped this electrode with a rare earth element called cerium, which improved how efficiently electrons move through the material during the reaction. The result: hydrogen was produced at 98.46% of the theoretical maximum. Formate was produced at roughly 89% efficiency. Both outputs remained stable over 60 hours of continuous operation. The circular part. Here's where the process becomes genuinely interesting for sustainability applications. The terephthalic acid recovered from dissolving the PET plastic isn't discarded. It's used as a raw ingredient to make more of the electrode coating itself. In other words, waste plastic generates the material needed to process more waste plastic. The researchers built and tested electrodes made entirely from recycled PET-derived terephthalic acid and found they performed as well as electrodes made from commercially purchased raw materials. After the reactions are complete, the remaining liquid can be processed further to recover two additional products: regenerated terephthalic acid powder, which could be used to make new plastic or more electrodes, and potassium diformate crystals, a solid compound used as a mold inhibitor in animal feed. The researchers recovered both through simple filtration and crystallization steps. Why this is different from regular plastic recycling. Standard recycling, the kind that happens when you put a bottle in a blue bin, is mechanical. The plastic gets shredded, melted, and reformed into a lower quality version of itself. Do it too many times and the material degrades to the point where it can't be used for much. It also doesn't recover the energy embedded in the plastic. Chemical recycling approaches, including this one, break plastics down to their molecular building blocks rather than just reshaping them. That means the output quality doesn't degrade, and the process can capture chemical value that mechanical recycling misses entirely. What makes this study notable is that it doesn't just break the plastic down. It links that breakdown directly to hydrogen production, turning a disposal problem into an energy generation step. The energy required to run the electrolysis is partially offset by the value of the hydrogen and formate produced. The honest limitations. This was a laboratory experiment conducted on small electrode surfaces. We're talking about centimeter-scale test setups, not industrial equipment. The jump from a lab bench to a facility that could process meaningful volumes of plastic waste involves engineering challenges the paper doesn't address. Running this process at scale would require consistent supplies of dissolved PT, larger electrochemical cells with more complex heat and fluid management, and markets willing to buy the formate and potassium diformate outputs at prices that make the economics work. Those aren't trivial problems. The 89% formate efficiency, achieved using actual dissolved PT rather than pure ethylene glycol, is lower than what the electrode achieves under ideal lab conditions. That gap exists because real plastic waste contains more impurities than a clean chemical solution. Understanding how that gap behaves as conditions vary will matter a lot before anyone invests in scale up. Why sustainability teams should pay attention. For organizations managing large volumes of pet waste, consumer goods manufacturers, food and beverage companies, apparel brands, the significance here isn't that this process is ready to deploy. It isn't, not yet. The significance is directional. Electrochemical upcycling is a class of technology that could eventually change the value equation for plastic waste. Instead of paying to dispose of or downcycle PET, organizations might one day recover hydrogen and chemicals from it. The incentives that would drive that shift, tightening plastic regulations, rising hydrogen demand, and ESG pressure on waste metrics, are already moving. Watching which of these lab-scale demonstrations attract industrial investment and move toward pilot programs is a useful leading indicator of where plastic waste management is heading. You've been listening to Sustainability Soundbites by Environment and Energy Leader. For partnership opportunities, please reach out to our team.